Hello everybody and welcome back. So in this next lesson I want to talk about noise. And noise is something that is often misunderstood or misused. A lot of people don't really know what's going on. It's very easy to use it in very basic ways, but to really understand what it can do at its most powerful, it's kind of neglected. So I'm going to try and show you what noise does and how we can work with it and think about all the different attributes that create noise, because we have to understand these if we're going to create noise in Vex. Okay, so in this particular lesson I'm just going to show you how noise really works, and then in the next lesson we're going to actually try and apply it in Vex, where we have to write out a noise function, and that can get quite complicated unless we understand what we're looking at. So I'm just going to show you my scene here. I've got a box and points from volume. Now you don't have to build this. I mean, you can if you want to play around, but I'm just doing this to visualize. I'm also isolating the top because I want to make a slice of this. So I'm dividing it by the same point separation. So you'll see here these are linked, and then isolating those points. So now I've got an identical sort of slice from the top of this noise, the top of this box, and I'm putting that in a group, merging it together. I'm applying the noise on top of one another, and then I'm offsetting just the box and not the slice using that group, and then I'm actually deleting the points that fall below 0 or below a certain threshold. So I mean, we'll be able to play with this number to see how the noise works as well, and we'll be able to also play with the number over here. I've got an offset for the slice, so we can actually move up and down through the noise. So these are all just methods of showing you what's actually happening with the noise. Okay. And I've also got my, under my geometry tab in display, I've got my point size set quite large. Oh, and then I've also got a gray background, just to kind of show this. Right, so this is what we're looking at, and this is all essentially to just show you what's happening inside of this node. Okay, which is, so I've got a point VOP where I'm creating some noise. Now the reason I'm using a point VOP is that the noise functions are already built in with all of their parameters exposed, so it's a lot easier. And having said that, it is easier to create noise in VOPs. So even now, even though I know how and can easily write a Vex expression for noise, I still just use VOPs every day because it's just easier. There's a lot of parameters when it comes to noise, and because of that, it's just simpler to do it in VOPs. However, if you're wanting to do some noise within a loop and noise within a PC open function and all of these things that are much lighter and much better to use in Vex, then you will need to write out a Vex function for noise. Okay, and it's not too difficult, but it's just when you want to quickly just jump in, throw some turbulent noise on something and write out a particular attribute, then VOP is probably the better way. Okay, and you're probably still going to use that after this. All right, so it's good to learn both methods, I'd say. Okay, because there will come a day where you need to do it in Vex. Right, so noise is basically, you need to think of noise almost as this like a field that's invisible and has values at every particular point within that field, almost like an extremely high resolution volume, where the voxels are almost infinitely small. So at any particular point you can sample a value within that noise field. Okay, and a noise field, you can think of it as being static and world based. Okay, so it doesn't move and it doesn't scale. What scales and moves is the position that we read within that noise. Okay, so the reason I've scattered some points in this box is because I want to show and visualize the noise as this kind of three-dimensional field within here. Okay, so basically within this noise field, the values from one area to another, here you can see the whole box in here, you can see where I've deleted the points. And this is just easier so that you can see through these black points over here. But basically, you know, this one point is going to sample a particular value. Let's pick a point here that we can see. So, you know, this point on the edge is going to sample one value. And then because this point is that distance away, it's going to sample a different value. And then that one will sample a different value and so on, right? And if we tell those points to sample values that maybe don't relate to their point position, then they're going to grab different values as well. So that's something else we're going to discuss, is how to use, you know, how to sample from noise but not using your point position, because sometimes that's not exactly what you want to do, right? So let's take a look at the type of noise we're using first and the parameters that we have available to us. Okay, so one of the most important things to understand about noise is this driver function. Okay, a lot of the times, like in here, we're going to call it position, but that's a little bit misleading because position does not need to be position. Okay, essentially it equates to the position that it should read from the noise field, but that does not mean that it has to be our point's position. Okay, each point could have a whole location of where to read, you know, within this noise field. Okay, so it's like if I had to say to each one of you, you know, give you a specific coordinate, like on a map, and then go to that map and then, you know, take a photo or collect a sample from there, maybe a soil sample or something, and then all of you came back and I gathered all the data and sort of mapped it out into this big noise function. Okay, so I could send you all just to exactly where you're standing. You know, if I had to stand you all in a row and say, everyone just bend down, pick up a piece of soil, and then we're going to see how dark that soil is or how rich it is with minerals or something like that, then we'd be able to chart it almost exactly like this on the left here, where each of you would have maybe a slightly different value. But the likelihood of each value being so vastly different that it just looks like noise, just looks like a random, you know, like every single point is different, is very minimal, because something like soil would, you know, there'd be patches where the soil would be rich and then it would fade off in richness. And that's kind of what I know that's a bit of a strange analogy to use in this case, but it's because in the real world you have noise. Things are not just different at every single point. They tend to have these patches of one particular value, whatever that value is. I mean, just like a cloud will have denser areas and then softer areas. It's not just that every single particle in that cloud is a random density. Okay, so this is what we're working with when we're talking about noise. Essentially, it's like a random, except that it's random based on kind of like a size and shape. Okay, like an undulating random shape. Okay, so this first position, like the first parameter position, is what we're going to mostly be working with to try and figure out how this influences the noise. Okay, we then have a frequency, which is actually a multiplier for the position. So if we change frequency, we'll see that the scale of this noise changes, right? We get smaller scale noise when we have higher frequency, or large scale noise when we have low frequency. And again, it looks like we're scaling the noise, but really what we're doing is actually scaling the incoming position. And we're telling that position, okay, you know, you, the point, actually live at this location in 3D space, but I'm going to take your whole position and scale it up or scale it down, and then tell you to read from the noise in that location. But you're not going to actually change your point position. You're just going to be reading from a different location within the noise. And that's what gives us the illusion of the noise function actually changing size, where in reality it's the coordinates that each point is looking within the noise that is being scaled. Okay. And then offset is similar principle, but it is about position. So it's basically saying to you, okay, I gave you a whole bunch of coordinates where to go and look on the map, but actually I want you to go to where I told you to go +1. You know, take a step to the left and then take that sample, right? So that's what we're doing here with offset, okay? And you can offset on all 3 axes at the same time or just one at a time, but you'll see it gives the illusion of the noise moving. Okay, it looks like our noise is moving upwards here. As I change the Y value, it looks like the noise is moving. But again, it is the position where we're sampling the value within the noise that is actually moving. Okay. Then amplitude is basically just a scale of not the coordinate position, but the actual sampled values. Okay. So as I increase amplitude, we're taking those values. If the this point was picking up let's say a 0.1 value, well, now it's going to be 0.1 times 5.19. Okay. This will also affect negative values, because you see here I am actually deleting, with that wrangle outside, I'm deleting all the points that are negative, that have negative values. Okay, so this particular type of noise, this Perlin noise, has positive and negative values, and as I scale up the amplitude, not only will the positive values get larger, but the negative values will also get, well, they'll get smaller, so they'll get, you know, further away from 0. Okay, and then we have roughness, which basically is it's almost like the degree of fall off between these values, right? So when we scale this down and have very not rough, so quite smooth noise, then you'll see, I mean, it literally does look smooth. It's almost like a blend or like a blur between all the values, so it interpolates between these noise values with much greater substeps, whereas here, as I scale up roughness, then it gets closer and closer to what we'd expect from just like a random, where each particle seems to be picking up a different value. There's very little interpolation between these. Okay, even so, you'll still see that there are patches. Okay, I mean, we could obviously take our roughness higher and higher, and eventually it would basically be a different value per particle. But yeah, it is still different to random, where each particle has a value that is independent of its position. Okay, and then the octaves here is essentially just almost the iterations of the noise applied. So it will go and apply this noise and then apply noise on top of the noise and so on, and kind of, I mean, it gives you similar results to something like roughness, although it seems to almost have a diminishing return. So 8 octaves is going to give you a similar result to 32 octaves, okay, whereas roughness is almost infinitely scalable. Okay, and then it's also important to note that you get different noise types, right? So in this anti-aliased noise, you only get the Perlin and simplex, right? But there is also a turbulent noise function, which we're going to be looking at, which has Perlin, original Perlins, sparse convolution, alligator, simplex, and then zero-centered Perlin noise. And then you also have a whole bunch of other types of noise as well. There's Voronoi and Whirly. So it's all just a different algorithm for how to calculate this kind of blobby, field, and then we sample within that field. And although the different noises are calculated differently and they have different algorithms, and some of them do not use something like roughness or octaves, they have either additional parameters, or some of them just don't use that at all, and they just use position, frequency, offset, amplitude. Okay, but at a foundational level, they're basically the same thing. Okay. It's just a field with different values, and we're choosing where within that field to gather our information. And if we understand that, then that allows us to do a lot with this, particularly if we have moving particles and we want them to have these kind of patches of different values, but we don't want those patches to be swimming. We don't want the points essentially moving through the field like this. If you look at my slice on the left, okay, imagine these were particles that I had simulated and that were dropping straight down. If we don't want those values to be swimming and changing like this, but rather to be stuck with each particle, then we need to handle the noise differently to if we did want this particular effect. Okay, so this may be what we want, and then great, then our noise needs to be based on position, because as our particles move, they're essentially sampling from a new position within the noise field, so therefore they're going to look like they're moving through the noise field being static and the particles being mobile. All right. But if we wanted this to just simply move down, or maybe these particles were simulated, to actually bounce off of other objects and or slide down the surface, and we want them to have these values stick, then we need to either create this before entering our DOP, or if we have a rest position, maybe a birth position for each of these particles, then if we use that position to sample from the noise, that position is not changing per frame, so the noise will not change per frame, and even though these particles would move, they would keep their own values, their noise values. Okay, so that's just one of the most basic examples of where you need to think very carefully about how you apply your noise. All right. So let's dive back inside here. I want to show you something about how we're going to alter this incoming position, right? So I spoke about frequency and offset being a multiplier and basically an addition to the incoming position. So I want to show you an example of if we don't change frequency, but we just multiply our position, and I'm going to multiply it by our time. So this is to show one that we can use driver attributes that are not only position. I mean, you could use just time if you want. In fact, let me show you what that would look like, right? So if we drive this noise using time, all of these particles have the same time. Okay, time is a constant, which is why it now just has one static noise value. All right, but this may be actually what we want. And then you'll see that as I hit play, we see it moving through that noise field. Okay, so instead of each particle getting a different value, they're all getting the same value, but it's still moving through that field. And you can see this by how it kind of fades from one value to another. And then, yes, sometimes it then suddenly dips below zero, in which case it gets deleted here. Okay, or if I switch off this delete, we may see this a little better. But you'll see suddenly sometimes its value changes very sharply, and that's based on the roughness. Okay, we saw that even within our the field we had before, some values it very suddenly just drops off and deletes, but others there's these soft interpolation between the patches. So this is what's happening here in time. And this is something very powerful, because often you want stuff to maybe be flickering, but you don't want it to flicker as in be random on every single frame, because then it's like a disco kind of flickering, where every single frame it's just like on off, on off, on off, on off. Whereas if you want the values to kind of almost fade in and out and jitter or whatever, then you could actually use a noise function to maybe even drive the amplitude of a light, like the intensity of a light. So very powerful to understand how we can use noise in different situations. I mean, here, if this was flickering too fast, well, we would just reduce the frequency of it. Because remember, if we reduce the frequency, then we're essentially scaling, it looks like we're scaling up the noise, or essentially scaling down our sample position. And our sample position is time, so it's just a linear value. So now this will sort of fade on and off, but but a little bit slower, like it'll stay a little bit more constant and gradually increase, decrease, except for the occasional little flickers where it hits a patch of noise where it's a bit noisier, a bit more rough. Okay, we could also reduce that roughness if we wanted and have these things just kind of fading in and out, but fading in and out at a random time. Whereas if we wanted it to be constant, we'd have to use something like a sine wave or whatever, fade in, fade out, fade in, fade out at an exact determined sort of rhythm. Okay, so let's take this back up to 0.5 and instead I'm going to take, so we're taking time, but we're multiplying it by the position, okay? And I want to use that to show you how we can get different values per particle, but, have it interact with another attribute and therefore achieve a different result, all right? And you'll see over time, as time increases, the frequency of the noise is increasing, okay? It's the same as me taking this and increasing the frequency, right? So that shows you exactly what I was saying, that basically the frequency is a multiplier of the position. So we're taking, instead of driving it in here, we're saying position multiplied by and then some other value, which is it's decreasing. So at 0, it's it's 0 time has passed, and then as we increase, more time has passed. Therefore, it's multiplying this value by a greater number. Okay, and then addition is going to be essentially the same as our offset. So if we let's plug this one in. So remember, that's just simply taking the position and then adding a static value. So again, our time is constant, right? And you'll see there the frequency is not changing. The size of these moving clouds has not changed, but they seem to be moving. Like we're moving through the noise field. Okay, the noise field itself is not moving, but the particle's sample position is. Okay, so this may be kind of the effect that you want. Sometimes this can be very useful when you want to be birthing particles randomly, or like use it as a source for pyro or something to create some kind of very random looking smoke. Okay, now I just also set up this little example where I'm adding and multiplying only one of the vector components. So we're just getting a vector component and setting the same vector component. I'm using component 1, which is x, just to show you a little bit more clearly that, see, the frequency only changes on the one axis if we do it this way. Okay, and same with addition. We can have it offset along the one axis only. Okay, so I hope this is starting to sort of show you, what noise does in a way that you can visualize what it's doing, because you need to kind of be able to imagine what the result is going to be, because often you're not seeing noise in this clear way. You normally don't have just a box full of points and you're watching the noise field move. You often have a much more abstract object, scattered points on there, and then you're applying a noise. And then you start wondering why you're not getting the results that you want. Meanwhile, maybe you're multiplying where you should be adding to the position. So if you're ever confused, maybe set up something like this to test what you're doing on something that's easy to visualize. Now here I've got a little example where I'm using something a little bit, I'm not even using point position at all. But because I know my point numbers are constantly increasing, so they haven't been randomized. So next to 0.0 is 0.1 and then 0.2 and so on. Okay, so I took my point number, I converted it to a float just so we can work with division properly, and I also took the number of points that I have and divided by that. So now it should literally be a 0 to 1 value that runs through my point numbers, and then I'm just multiplying this by a constant so that I could alter the frequency of this, and I get kind of a cool, funky, like very technical looking effect. Like if you wanted something for you know, like a computer, you know, system kind of weird effect, then you could do it like that. So see, I'm just plugging that straight into my position there, and because we're feeding it these kind of random weirder numbers, it's sampling still from that same noise. I mean, we can, you know, we can change the frequency here, or we can offset it so you can see it kind of moving through. But the result is obviously going to be vastly different because of the position that we're feeding it. Okay, and if we go over here, you'll see this kind of, you know, this could give you quite a cool effect. You know, you could rasterize these, you know, turn it into a volume, maybe find the edges and highlight those, and then you've got that almost like matrix kind of effect. Okay, so just showing you different ways of driving that, and I've got a little example here as well that will hopefully help as just understand a little bit more. So I've got a sphere with quite a lot of points, just so that we can see it a lot better, and I'm calculating normals. Got another sphere, also calculating normals, and I've moved it in position, and I've got it animated, just kind of moving around the sphere just slightly. Okay, and what I want to do, what I'm doing in here in this wrangle, is I'm calculating the dot product of the nearest point on the surface, but I'm using XYZ dist, so it's not grabbing the actual point, the nearest point, but rather the nearest location, which could be in the middle of a primitive. Okay, so it's essentially grabbing a primitive number and a primitive UV. In other words, it's the same as doing a raycast node, and we are going to talk about that in the future and actually rebuild the raycast node bit inside of Vex. So don't let this confuse you for now. But basically, I'm grabbing the nearest location on this other sphere, and then I'm running a dot product. So the dot product is essentially saying which direction it's facing. So are my normals on this sphere, when I find the closest point on this sphere, are my normals facing it or facing the opposite way or facing 90 degrees? Okay. So the result of a dot product, if you've never seen one before, will look something like this. So I'm just going to unplug that and feed this driver attribute directly in. Okay. So the dot product value will look like this. It's a -1 to 1 value. So if I fit it here between -1 and 1 to a 0 to 1 value, then we can see all of the values. And you'll see here where it's close to touching it, it will be values of 0, because also where it's facing the other sphere, those normals are facing each other almost directly. Okay, and then as the sphere falls off and the other sphere falls off, then this will be sort of like an exponential fall off. Okay, and I'm using that as a driver attribute for my noise. Okay, so now you can see, and you see I'm not putting the fitted value in here, although I can, but it'll just have changed the frequency really, because you can feed negative values into noise as a driver. So I'm feeding the value in, and so because that was a smooth gradient, but that gradient, similar to time, is showing, you know, sort of, it's a linear set of values which are then feeding from, like, reading from this noise. So now along that smooth gradient, I have some sort of, you know, peaks and troughs of this noise. Okay, similar to how a sine function would be, except more random. Okay, so we can use this to create some maybe almost like ripples of noise. Okay, so I'm using this, but then I'm going to just take my point position and add my normals, but my normals multiplied by the noise. And then also it was a little bit more too intense, so I just multiplied by a constant to bring it down. And the result is here we have, if I hit play, we have ripples moving along the sphere outward from the closest point on our second sphere, which is animated. Okay, so you'll see we have now sort of these outward moving ripples. Okay, so you can use noise in a variety of ways to create these really kind of strange effects, not just to, on a flat surface just give random, color values or something like that. You can actually create, ripples, ocean waves and things like that using noise. You just have to feed the right driver attribute into it, okay? Keeping in mind that the driver attribute does not have to be your point position, okay? It's the position to read within the noise, but if you feed it a linear value, then it's going to read like this, a linear value across the gradient. Okay. Right, so I hope you guys enjoyed that lesson, and I hope that you're understanding noise a little bit better, because in the next lesson we're now going to actually dissect all of those parameters and create noise in Vex by writing it all out. Okay. Right, so I'll see you guys in the next lesson.